Using rectangles is one way to approximate the value of an integral. Another way is to use trapezoids. I'm going to zoom in here. We have the same function and the area from under the curve from A to B. And I'm going to build a trapezoid here. For this trapezoid, I still want to consider the ith subinterval. We still have x sub I minus 1 and x sub I, and a width that is delta x, which is b minus a over n. When we set up the fundamental units, though, using trapezoids, we have a slightly different formula. If we isolate this trapezoid here, we can see that it's got, well, the height is delta x. The long base is the function value at x minus 1, so f of x sub I minus 1. And the short base has a function value of f of x sub I. Generally, we refer to the bases of a trapezoid as, say, like B2 and B1. And with that notation, we would say that the area of a trapezoid is equal to the average of B1 and B2, so B1 plus B2 over 2 times the height, which is also sometimes written as h over 2 times the quantity of B1 plus B2. In terms of our function and the integral that we're going to be approximating, a sub I, the area of the ith trapezoid, is going to be equal to delta x over 2, because that's the height, over 2, times f of x sub I minus 1 plus f of x sub I. And you'll see I rearranged the order of B1 and B2, but it's addition, so that's fine. With this as our fundamental unit, we can now look at the trapezoidal rule. It says that the integral from a to b of f of x dx is approximated by t sub n, where t represents the trapezoidal rule and n is the number of subintervals that we're talking about. And it equals delta x over 2, that's the h over 2, times the quantity of f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus plus 2 times f of x sub n minus 1 plus f of x sub n end bracket. Now you may be wondering where the 2's are coming from. I'll get to that in just a moment. But I'm going to need to continue the sentence here and say all of that where delta x is equal to b minus a over n, and x sub I, the inputs, are a plus I times delta x, like when you first saw integrals. Now about these 2's, there's actually a pattern that I want to write down for the coefficients. And it is that the coefficients are 1, 2, 2, 2, 2, dot, 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 2, 2, 1. Why the 2's? Well, if we go back to our diagram here, if we look at the the trapezoid that's just to the left of the one that we were just looking at, that trapezoid has a long base and a short base. The shorter base is actually the same as the longer base of the trapezoid we were just looking at. So that particular height is used twice, once for the pink trapezoid and once for the green trapezoid. And as a matter of fact, all of the heights of the interior trapezoids are going to end up being used twice. But the endpoint trapezoids have heights that are only going to be used once, and it looks like I missed one of these heights. So because all of these interior heights are going to get used twice, we write down 2's for the coefficients of the interior trapezoid height dimensions. And just to double check that we're all on the same page here with the a plus I times delta x, a is the left endpoint of the interval. The first value x sub well, I wrote x sub I. X sub 1 is delta x away from a. And then after 2 instances of delta x, we're at x sub 2, right? So that's where the I plus, or a plus I times delta x is coming from. Just as with the midpoint rule, the trapezoid rule has an error involved as well. As you can see, the trapezoid is not exactly capturing the curve of the function. Error for the trapezoid rule, or I should say the trapezoidal rule, is absolute value of e sub t is less than or equal to k times the quantity of b minus a cubed divided by 12n squared, where again the absolute value of the second derivative of f of x is less than or equal to k.